I can see Kiril Maltsev is there. Can you please activate your microphone? We can check the connection now. Okay,
I'm here just to check that the connection works well.
Yes, I make you presenter, so you can share your screen now.
Yeah, just to check whether it works. Yes.
Yeah.
Mm-hmm.
Okay.
Hold on.
So you can show the presentation. Okay. Okay, we can see it. Works perfectly. Can you change the slide? Okay, yeah. It works. Thank you so much.
Yeah, great. Mm-hmm.
Okay, now we are going to start the session. The first speaker of today is Professor Ashtekar. So I'm going to make you presenter now. He will speak about quantum gravity. And can you, yes, you just show the presentation. Okay, you can go on. I will warn you 5 minutes before the time of the end of the talk, okay?
All right, okay. So let me go to the full screen mode. Is it okay? Can you see everything?
Yes, yes, perfect.
Okay. So the title is Quantum Gravity in the Sky, question mark. Can we see effects of quantum gravity there? Let me see if I don't be able to do my cursor, but that's life, huh? Let me just get out of here and see if I can use my cursor. Yeah, is this better? I can use a cursor. In the other mode,
yes,
I cannot use a cursor.
Sure. You can use also. Try to enlarge it a little bit if possible, but otherwise it's okay.
Yes, okay. No, that's too much. Okay. All right. So the quantum gravity in the sky and alleviating the tensions between C and B and the Planck scale physics. And the point up here is that I would like to talk about loop quantum gravity. There is a lot of work on loop quantum gravity, but because my time is limited, I'm not going to give you an overview, but I'm just going to sort of present the work that is based on a recent physical review letters that were just published last month, which is up here. So as I said, I'm going to use loop quantum gravity to extend the standard inflationary paradigm. And the goal of this is to show that somewhat surprisingly, Planck scale physics helps alleviate the tension between theory and observations vis-a-vis anomalies that are seen in the C and B. In particular, the power suppression anomaly and the so-called lensing amplitude anomaly. I know that the audience is mixed, and so they may not know what these things are, and I will explain. What we use is just a flat Friedmann-Lemaitre-Robertson-Walker model with inflationary potential, but we embed it in the framework of loop quantum cosmology so that we can also treat the Planck regime. And then when we do that, there is no Big Bang. There is actually a big bounce instead of Big Bang, and physics is all regular, so we can handle the early universe. And therefore, we have a pre-inflationary dynamics phase of loop quantum cosmology, which is completely regular, no singularities. And there's a proposal that has been made for the choice of the background geometry, that is to say, what will substitute the Friedmann-Lemaitre-Robertson-Walker model, but the quantum analog of the geometry, and for the perturbation, the cosmological perturbations, which propagate on this geometry. And what we'll do is to constrain the choices of the background quantum geometry and the state of the perturbations using loop quantum gravity considerations. And what we find is, when we have done all these things, then we can calculate the observable predictions, and we can see that the loop quantum cosmology predictions provide a better fit to the observation data. In particular, two of the anomalies are naturally resolved, and there are also testable predictions for future observations. So let me just, since the audience is mixed, let me just explain how this is done. So with the Planck satellite, how do we determine which lambda CDA model we live in? In this analysis, the lambda CDA model is characterized by 6 parameters. Now, one makes an ansatz. I want to emphasize that this is an assumption which is made, which is very well motivated from inflationary scenarios, but it's an assumption that the power spectrum will be nearly scale invariant. And it's a pleasure to explain this in this particular conference because these ideas really originate back to Zeldovich. And so the power spectrum is given by an amplitude times the wave number divided by fiducial wave number multiplied by ns by ns1. So depending on the value of ns, either the power grows as k increases or power decreases as k increases. Ns is less than 1, and therefore the power actually increases as power actually decreases as k increases. So this is called blue tilt. And ns is called the spectral index. So the 2 parameters are in red up here, and that is a standard ansatz made about the primordial spectrum. But then these primordial spectrum of the perturbations propagates. And between the end of inflation and the surface of last scattering, there are 2 parameters that govern the physics and the astrophysics and the astrophysics, the omega baryon and omega cold dark matter, the density of these matter fields, and then propagation from the CMB surface to us is again governed by 2 other parameters which go under the name of 100. It is 100 times basically the angle of a mega cluster, and this is really given. This is the baryon acoustic oscillation length. That is what it encodes, and then the reionization optical depth tau. Given these 6 parameters, we get a particular lambda CDA model up here, and then basically we can, given these 6 parameters, we can use the Boltzmann equations from astrophysics and the CAM code. Then that gives us predictions for observables. And the observables are the correlation functions, temperature, and we see them in the sky. And what we do is a YLM decomposition. It only depends on L because it's a correlation function between 2 points. And really what matters is the L, the M, which is so to say goes around the line that joins these 2 points is you get the same power spectrum. So you get CL of TT, this is temperature, then electric polarization, then the cross correlation between the temperature and the electric polarization. And then finally, there's something which is called a lensing amplitude. And therefore, what we can do is, given these parameters, we get these predictions, and we can take this and compare them with the data. And when we compare with them with the data, we obtain the best fit with the data provides us with best fit for the 6 parameters and standard deviations or the error bars. And that is what determines the lambda CDA model that we're supposed to live in. So as everybody knows, this model has been this lambda CDA model idea has been extremely successful, and this particular procedure has met with spectacular success in terms of what everybody has seen many, many times, not only the cosmic microwave background, but also all these various peaks that we've seen there. They are completely faithfully represented by the model. But as you can see here, for lowers, this is a big scale up here, up to here, about L equal to 50. It is a linear scale. That's what Planck does, because here some more non-trivial things happen. And after that, the theory and observations really agree with each other very much. And so this is logarithmic scale up here, going to about 2000 up to 3000. You can beyond 2000. And so this is really very nice. And then this model also predicts other observables. not the ones which are used to determine the parameters, but additional observables like the lensing amplitude and the B mode polarization spectrum. So these are new observables, and there are predictions for these new observables, and therefore which you can independently test them with future observations. But as we already see here, while the agreement is very, very nice for large L's, for L less than 30 up here, the agreement is not so good. And this can be codified completely by what is called a function C of theta. So instead of doing the YLM decomposition, we can just look at the power as the angle of theta. This is a correlation function between 2 points. So the angle theta, which relates those 2 points, is what one is looking at here in the sky. And so the statement up here is that what we see here is the following. The standard ansatz, the standard inflationary model, predicts a C of theta power spectrum, which is in red. And the Planck data, on the other hand, gives us the curve which is in black up here, and these dots are the observation plots up here. And we can see that there is a discrepancy between them. And there's a quantitative way of characterizing the discrepancy. This was a subject which was really pursued over many years, certainly starting from WMAP, and leading cosmologists who work at the interface of theory and observations have worked on it. And some of the names are here. This is by no means a complete list. And they suggested that we can calculate this observable, which is called S1/2. And that is really integral from -1 to 1/2 of d cos theta, if you like, and here the usual volume element on the 2 sphere times C of theta whole squared times the power squared up here. And it is 1/2 because we are looking at angles which are larger than 60 degrees all the way up to 180 degrees. So that's what we're looking at up here. And then the statement up here is that there is this discrepancy. And then there's also another anomaly, which is associated to the lensing amplitude that I told you about. By assumption, by the construction of the model, the lensing amplitude is supposed to be 1 up here. But the standard ansatz and the best cosmological model that we have today, the lensing amplitude, the value 1 is outside the 1 sigma of the lensing amplitude. And it is incompatible with the lambda CDA model in the sense that it is outside 1 sigma. It is within 95% confidence level, but not within the 68% confidence level. And people then try to modify the lambda CDA model by adding a spatial curvature. And they found that when you do that, you can actually bring the lensing amplitude into value 1 into 1 sigma, well within the 1 sigma. But then when you do that, there are other problems at low Z, and there are new tensions that arise. And therefore, the point is that the general belief is that there is actually a tension between cosmological model that we have today and this lensing amplitude. And this led to a suggestion by these authors, Valentino, Mareschi, and Joe Silk, Melchiori and Joe Silk, to a suggestion that there is a possible crisis in cosmology because of these anomalies. So why are the anomalies interesting? I mean, the point is that the statistical significance of any one anomaly is low. As we saw, it is between 2 and 3 sigma. So it is it's not very high, in the sense that if you were to actually do realizations from your theoretical model, so theoretical model provides a probability distribution, and you can look at various realizations of this probability distribution. And if one finds that there are the given model actually occurs in 1 in 1,000 realizations, that is typically considered as all right. But if it becomes 1 in a million, then it's considered not to be good. And any one anomaly, it will be 1 in 1,000 realizations. But if you want a universe in which 2 anomalous features are realized, then the probability goes down significantly, and one finds such a universe only in a 1 in a million realizations. And that is why then, do we really live in such an exceptional universe is the question that arises. And therefore the Planck in the release of the 2018, in the first paper itself, pointed out that since if any of the anomalies have primordial origin, then the large-scale nature would suggest an explanation rooted in fundamental physics. Thus, it is worth exploring any models that might explain the anomaly, or even better, multiple anomalies, right? Because the probability of living in a universe in which there are two anomalies is very low. So if we can explain such anomalies naturally or with very few parameters, then that would be something that is really interesting. And therefore, we get an opportunity for us, is an opportunity to connect quantum gravity with observations. So what happens in loop quantum cosmology is the following, that there is a standard ansatz that is used, as I said, in transparency, in the very early transparency, we use the standard ansatz up here that is motivated by inflation. But what happens in loop quantum cosmology is that that standard ansatz is actually not realized. There are corrections at small k's or at large wavelengths. And it is such that the predictions of LQC agree with the standard ansatz for high k, but there is a specific power separation at low k's. And this result is in alleviating the two of the three anomalies, and that's why it is considered as interesting. And that's why it was written up in several news media in the last month. So what about loop quantum cosmology? So that's what I want to tell you now about very briefly. It's a long story. It goes back to about 20 years or 15, more than 15 years, 15 to 20 years, and a lot of people who have worked on it. The key points for this talk are just that the Big Bang singularity is resolved. Instead of talking about a classical metric, we talk about a certain wave function in the mini superspace of this classical metric. And then the quantum perturbations propagate on this classical metric. But before we go to the, on this quantum geometry. But before we go to the quantum perturbations, one can also ask that if in fact there is inflationary potential, then would an inflation with sufficient number of E-folds or arise naturally? And it does arise naturally because of pre-inflationary dynamics. So that is one of the interesting results. And then as far as the quantum fields, which are in the cosmological perturbations, are represented by quantum fields in all the models, also in standard inflation. These propagate now not on a classical background, but rather on the quantum geometry that is given to us. But there is a very nice result which says that so long as one works with sharply peaked states up here, then the propagation of these perturbations is well characterized, is well described by propagation of the perturbations on a certain dressed effective metric. So this makes the calculations very possible, feasible, and the detailed analysis has been carried out. But to carry out this detailed analysis, we need to have a certain quantum states of the background as well as of perturbations. And therefore, there has been a proposal to how to select these things. As far as the standard inflation is concerned, one starts in a phase of the universe, so to say, not in the standard inflation, there is a Big Bang. One starts not at the Big Bang because one cannot, everything is singular, but a little bit later. And just before the slow roll begins, one assumes that the state of the perturbations is in a Bunch-Davies vacuum. That's an assumption which is motivated, but it's an assumption. In loop quantum cosmology, we want to really start in the Planck regime, and therefore we need to specify these states. And again, we need to make some assumptions, but these are motivated now by quantum geometry. And these were spelled out in a paper up here. And that these assumptions tell us what kind of states we should use for the background geometry, and what kind of state we should use, Heisenberg state we should use for the perturbations up here. And for background geometry, this particular way of fixing the state, it actually leads to a geometry in which, roughly speaking, there are 141 E-folds for the bounds till today. And for perturbation, fixing the Heisenberg state of the quantum perturbations using the Planck scale dynamics of LQC, and then maximum allowed, what one asks is that there should be maximum allowed in homogeneity and isotropy, but quantum mechanics introduce uncertainties, and because of vacuum fluctuations, we cannot have exactly entirely homogeneous isotropic universes. But then there is a condition that is inspired by Penrose's wild curvature hypothesis. This hypothesis was made in classical relativity, and it has been elevated to quantum geometry. So when this is done, we can make predictions. So what are the predictions for the various observations? The first prediction is that there's a power suppression at the primordial level. The standard answers I told you was like that, where there are two parameters, AS and NS. And this is really very well achieved up here, where in fact the K is sufficiently large, if you like, if in the angular moment, in the spherical harmonic decomposition is bigger than 30, then in fact there is very good agreement with standard inflation. But when L is less than 30, for small wave numbers or for large wavelength, this is really modified. This is a standard inflation. And then what we obtain up here is something which is the power is suppressed up here by a specific factor up here. So f of k is equal to 1 for large k, but for small k, there's a power suppression. And there are analytical results which suggest that this result will, this was done specifically for the Starobinsky and the quadratic potentials in great detail, but there are results which suggest that this will hold for a large class of inflationary potentials. Well, what we had this primordial power spectrum, and we want to convert this primordial power spectrum exactly as we did in the very first transparency. The primordial power spectrum is converted into this power spectra. So that is what we do now. We want to convert it to this power spectrum. And for the TT spectrum, as you see, for L bigger than 30, we get the standard ansatz or standard inflation LQC is the same, and they all agree with the Planck data. But in fact, for low L's, there is a power suppression in LQC, and the agreement with the Planck data is actually better. Now, this may not be obvious that the agreement is a little better. Therefore, we can go, as was emphasized by the cosmologists, that the better measure is to the CF theta. So we can go and look at what happens to CF theta. So as I said before, this is the prediction of standard inflation with the standard ansatz for the power spectrum. But LQC says that the power spectrum is modified at low k, at large wavelengths, or therefore. And then the statement is that what we obtain up here is a suppression, power suppression up here, and this is the prediction. The blue is the prediction of LQC up here, and then the black is the actually measured of value up here. So for S1 and 1/2, which is a quantitative measure of power suppression, we see that for the standard ansatz, standard inflation, it predicts 42,500 roughly, whereas in LQC, it is reduced by a factor of third. But it is really, so 2/3 reduction, and it is really 14,300, roughly speaking. So in fact, this now is not anomalous. It is well within 1 sigma, within 1 sigma. Now, what happens with the lensing amplitude anomaly? So what we can plot the lensing amplitude versus the optical depth up here, which is the reionization optical depth parameter tau. And in lambda CDM model, the assumption is that AL should be equal to 1. So it should be equal to 1 up here. Now the prediction that I gave before, which was supposed to, which for the standard ansatz, which is in red up here. So that prediction is this contour. The two overlap, and therefore it becomes violet. But that prediction is this contour, and this is away from the value 1. The prediction of LQC on the other hand is the blue one. So then the prediction up here is this contour, which tips down up here. And therefore one can see that the value 1 is well within the 68. This is 68% confidence level, well within the 68% confidence level. So whereas it was outside the 1 sigma contour, 68% confidence level for the standard answers, which had led these authors to introduce spatial curvature and then suggesting that there's a crisis in cosmology does not occur. There is no crisis whatsoever. So what about the cosmological parameters? Well, 5 of the cosmological parameters, their values are not changed by the loop quantum cosmology correction at all, but the optical depth is increased by a factor of 10%. This is, of course, changed, but it's changed very little, these 5 parameters. So these 5 parameters you see up here, you can see that the differences between the two are very small. But for the optical depth, it is really 542 to 595, and this is about 90.9.8% or almost 10% increase up here. And this really is the important reason why the lensing amplitude is that this anomaly is actually removed. And then S1/2, as we said, it is decreased by a factor of 3 from about 42,500 to about 14,300. Now, future observations are expected to provide independent measure of this optical depth. There are planned missions which will actually measure this. And there are also planned missions which will actually measure, for example, the odd parity polarization, the bipolarization, and there are predictions also for loop quantum cosmology which differ from standard answers. So hopefully they will be measured. So let me now therefore summarize. We got quantum gravity in the sky. So I began with this particular quote from Planck saying that since any of the anomalies have primordial origin, then their large-scale nature would suggest an explanation rooted in fundamental physics. Thus, it is while exploring any model that might explain the anomaly, or even better, multiple anomalies, naturally or with very few parameters. We have a concrete realization of this idea in loop quantum cosmology. There is separation of power at large angular scales in CMB, and therefore better agreement with the data than standard inflation. And the power separation anomaly is thus alleviated. And similarly, the lensing amplitude anomaly is alleviated, and therefore we got potentially, and furthermore, we got potentially observable consequences for the optical depth and also for the B-mode polarization of other observables that can be calculated knowing the lambda CDA model we live in. So LQC would say that we do not live in exactly the same lambda CDA model as was predicted by standard inflation. 5 of the 6 parameters are essentially the same, but optical depth is increased by a factor of 10. So in the year, as there are 2 anomalies which are explained, so they were emphasizing multiple anomalies, and naturally, or with few parameters, there are no few parameters needed. There are principles which select the states, but there are no parameters that are introduced here to match with the data. There are other mechanisms to invoke power separation, but they rely on additional parameters or features in the potential, for example, fast roll inflation, fast roll just before the slow roll starts, and so on. And we are not tweaking the potential. We're not doing anything like that. It really is coming out of what is happening to corrections at the Planck scale. So there is a symbiotic interplay between the fundamental theory and observations. Thank you.
Thank you so much for this inspiring talk, Professor Ashtekar. There are several questions. There are several questions, and we start with the question from Andrew Beckwith. Are the anomalies at low L an artifact of having a singularity at the start of lambda CDM? Certainly, LQC appears to provide an answer to the problem, but is the existence of a Penrose-style initial singularity part of the main reason for the existence of the problem in the first place?
So I would not have any reason to really, that will lead us directly to this conclusion that because there is a singularity, then there must be anomalies. Because there are many assumptions, as we saw in the transparency one. The framework really goes into many things. Oops. One first makes the standard ansatz. So you could keep for example, we could keep the singularity. Inflation starts afterwards, and we could just modify the standard ansatz. But then one would have to give meaning. One would have to give reasons for actually modification of the standard ansatz. There are no obvious reasons to give this modification. But if one came up with such a modification, then even with singularity, it is the anomalies will be alleviated. So the strength of LQC is that it really does several things at the same time. It is not that singularity resolution automatically gives rise to the alleviation of anomalies, but rather that LQC does both. It resolves the singularities that enables you to give the initial conditions, the Planck regime, if you like, choose states using the Planck scale physics, and then do evolution in the Planck domain. And that is what alleviates the anomaly. So the strength of LQC is really that there's a nice global picture.
Okay, thank you. And there is another question from Partha Sarati Majumdar. Actually, it's two questions. First, do you have to assume the inflationary potential, or does it emerge from LQC?
So currently, we are assuming the inflationary potential, so it is put by hand. The quantum corrections are pretty insensitive to the detailed choice of the potential. So long as the bounce is kinetic energy dominated, we believe that the features I presented will all be there. We have done very detailed comparison between the predictions of two potentials, namely Starobinsky and the quadratic one, and in both cases, the answers are exactly the same. Now, however, I mean, there's a hope in the back of all these things, which is that what we have done so far, what we have done is not really sort of taken into account full loop quantum gravity. We have only looked at it in this context of this symmetry reduced models. And the hope is that maybe the quantum corrections will actually give us something like the scalar curvature correction to Einstein's equation. And that scalar curvature correction to Einstein's equation, then as Starobinsky taught us, will actually lead to the Starobinsky potential, and therefore all this will happen naturally. But this has not been realized in great detail. In particular, for this to be realized, we would need the coupling constant in front of the scalar potential to be much smaller than what it normally would appear. And work is in progress to understand if, in fact, there is some mechanism which would give us the appropriate value for this particular parameter. But this is work in progress. There is no definitive result.
Okay, thank you. And there was another question from the same participant. There are non-inflationary models which also involve the big bounce. How do their predictions differ from yours?
Right. So, I mean, it really depends. Very good. So just having there being bounce does not necessarily mean that there will be reduction in the power spectrum or the lensing anomaly would be alleviated. However, there are actually certain there are certain features which are kind of generic features. If the bouncing models share these features, then the anomalies will be alleviated. If they don't share these features, then they will not be alleviated. So basically, if it turns out that there is a power separation, and this is not guaranteed, if there is a power separation at low L's, then in fact, because of the reasons that are given up here, then it turns out that the best fit value of the optical depth would be larger, as happens in LQC, and the lensing amplitude will be lower, as happens in LQC. So then there is a tendency to alleviate the anomaly. But whether the power separation, there will be power separation or not, is not clear. And also, this is just a qualitative statement. One would have to really check that everything, for example, the lensing amplitude anomaly is relieved. In other words, the value 1 is brought to 1% or to 1 sigma level, and that is not guaranteed.
Thank you.
Thank you,
there is last question from Kiril Maltsev. I just put it short. How about other types of anomalies, such as the set of concentric low variance rings, as pointed out by Gurzadian and Penrose, and the Hawking points, as pointed out by N, Messier, Penrose, and others in 2018? Do LQG, actually C, corrections also achieved to account for those?
Well, I think there's a paper by 2 of the postdocs at Penn State that was written about 2 or 3 years ago. One of the names will be William Nelson, which point out that in LQC, basically any bouncing model which will give rise to the features which are the circles in the sky that were pointed out by Gurzadian and Penrose. Now, whether this is statistically significant enough to call anomaly is being debated much. That's why I did not really include it. But one anomaly which is there, which I think people also talk about, that is statistically significant. But that, I mean, again, like 2 to 3 sigma level is not huge, but still is the hemispherical anomaly. Namely, the power is not distributed uniformly in the 2 hemispheres. You can cut the celestial sphere in such a way that the power in the northern hemisphere is different from power in the southern hemisphere. Now, this is something that is also relieved by LQC, not by the paper not in the paper that I talked about, but there's very interesting work by Ivan Aguio, Vijay Kumar Srinath, and others, which actually address non-Gaussianities within LQC. And they show that as a result of appropriately handling non-Gaussianities, the power suppression anomaly is also alleviated. We are currently trying to understand if, in fact, calculate the non-Gaussianities in this particular framework that I just told you about, and whether the results hold or not is not clear. But qualitatively, there are reasons to believe that not only will the results hold, but they will actually be improved. Okay, thank you.
Thank you very much. Okay, let's thank Professor Ashtekar again. We are going along with the program, and we invite the next speaker, who is Vladimir Soloviev. Can you please share your screen now?
Can you see it?
Yes, we can see your screen. You can go on. I will warn you 5 minutes before the end of the talk. Thank you.
Thank you. Maybe 2 minutes are free because my talk is...
Okay, 2 minutes. Okay.
So let me express my gratitude to the organizers for this nice meeting. I am happy to be here. And I will speak about bigravity. It means modification of a general relativity, which contain 2 metrics instead of 1. And this modification has a long history, starting from very long ago. But first, 1 metric was treated as background and not dynamical. But in the last paper, given here by Hassan and Rosen, it was proposed to consider both metrics to be dynamical. And so the construction of Lagrangian is very simple. We take 2 copies of the general relativity and with some matter minimally interacting with 2 metric tensors, and we add to them a potential to organize the interaction between them. And this potential, of course, is interesting, but first I should say that I am speaking about Hamiltonian treatment. And so in the Hamiltonian picture, we consider space-time as foliated by some hypersurfaces, which means states of the gravitational fields. And so these hypersurfaces are evolution of them is a transformation from one hypersurface to another. And the main point here is the so-called lapse and shift functions, which are simply decomposition of a vector connecting 2 points with the same spatial coordinates. And so this can be considered as a part of a world line of some observer. So it is decomposed into a normal component and into the tangential component. And so we have function of lapse and shift, very well known. But in bigravity, we have two space-time metrics. And so we have two normal vectors to a given hypersurface at any point. And for example, we have two light cones, for example, red and blue here. The only thing we should be worried about that this time-like section should have enough intersection between two of cones, and the spatial space-like, also has enough space to be common. Then this Hamiltonian formalism will have sense. In other cases, it will not have. Then let me say that Karel Kucharz long ago considered the covariant approach to the Hamiltonian gravity for general relativity, in fact, but it is very simple. He introduced not the only ADM coordinate system, which is correlated with the family of hypersurfaces, but he introduced also arbitrary coordinate system in space-time. And so the hypersurfaces are given as embedding by these functions I. So then we can introduce two bases. One is based on metric G mu, for example, and the other on the metric F mu. And we have different bases. So each matrix can be decomposed into normal and tangential parts according to its basis. Here, the only dynamical part, as you can see, is gamma ij or eta ij. They are induced metrics on the hypersurface. Then the other variables are lapse and shift functions for each of the metric. And if we treat everything in one basis, for example, this basis is based on metric F mu, then we obtain the combination of two metrics, which is necessary to construct the interaction potential. We can decompose this combination, and we see that it is a peer-induced metric, and also some functions which are ratios of the lapses and shifts. But if we only construct invariant polynomials, invariants of this matrix Y, we come to the known difficulty called as Bowler-Desert ghost. So it appears because in general the potential will be nonlinear function of this U. This U is substitute for lapse function. So we have a lapse function of one metric and shift function of one metric as in the same role as in general relativity as arbitrary functions, but here U and UI are additional arbitrary auxiliary functions, and we should vary action in them. And so we have not enough constraints to get the number of degrees of freedom we want. But these three scientists proposed a new formula for potential. Really, it is based on the square root of matrix Y, and we call this square root as matrix X. And the potential is the combination of the symmetric polynomials of this X matrix. So these are the symmetric polynomials. They could be expressed through eigenvalues of a matrix, or as traces of this matrix and of its powers. Then the composition, I have already given, the composition of matrix Y is this one in the basis, but after the Hassan-Rosen transformation of variables, it is possible to write not only Y matrix, but also the square root of it. It is possible to find an explicit formula for the square root matrix, and it contains really this U mentioned above and this new variable V instead of UI. And also it contains a combination of this V and new matrix D. This new matrix D is again implicitly given because there are no explicit formulas for this matrix D. And the problem to work with such a potential is not easy. So you can see a list of papers for 10 years, and you can see different authors who has participated in the problem, in the solving this problem. There are some difference. First approach is based on the implicit function D. The second approach is based on tetrad or Yerbain variables. You can see that the most active this field was about 4 years. Then it was some break, but 2 years ago there were interesting papers written by physicists from the Stockholm Institute, Hassan, Lundqvist, and other paper by Kosic. You can see these persons here, very nice. And what they do, they solved the problem, the hard mathematical problem with the implicitly given matrix D. They were able to use the equations which we have for this function D. In some sense, we can understand it as D is very crudely a square root of matrix gamma, but not so simple square root. And they have done all the calculations of this formalism, working only with these equations and with function as given implicitly. But there is another way. Another way is based on the tetrad approach. It has started from the paper by Hinterbichler and Rachel Rosen. And the idea is that tetrads or Yerbains are in some sense square roots of the metric. And we have two metrics, so we have two square roots. One tetrad will be denoted here by E letter, another by F letter. And if we substitute the expressions for the metrics in terms of tetrads, into under this square root, we can see that it is possible to get a quadratic expression under the square root if we suppose that there is symmetry conditions fulfilled. If symmetry conditions of this form are fulfilled, then we have explicit formula for matrix X, which is a square root of matrix, but not a square root in tetrads.
And you have 2 minutes, sorry.
Thank you. Thank you, but it's not my calculation, I'm sorry. So the main idea that we have now, take tetrad and we make something like gauge. So one leg of one tetrad is fixed as a normal vector to the hypersurface. And of course, another metric cannot be given in this way. And for another metric, for the second metric, we should add some variable. So when we project tetrads on the spatial hypersurface, we have triads, in fact. So they are triads, but there are additional 3 degrees of freedom, and we introduce momenta for them. So they are treated as canonical momenta. Then everything is becoming fine. We can get the algebra of constraints. There are first-class constraints responsible for the diffeomorphisms of the space-time. There are 3 first-class constraints responsible for the rotation, spatial rotation of tetrads. And we have a lot of secondary constraints, second-class constraints, but there are important 2 of them, which are killing just the Gauss degree of freedom. They are named by S and omega. So we have algebra for them, they are Poisson brackets. And the important point is that in the standard Dirac procedure of working with constraints, we obtain the symmetry conditions, tetrad symmetry conditions. Now they are derived and not introduced from the outside. And also one of these symmetry conditions, one part of these symmetry conditions really is just the celebrated Hassan-Rosen transform. So it is now derived and not guessed. And here you see the special constraints, second-class constraints, which are special for the tetrad approach. There are 12 of them. And this is a table where we see calculation of degrees of freedom. So these degrees of freedom occurs to be 7, as it should be for the bigravity, 2 degrees of freedom for massless tensor field, and 5 for massive gravity. And here I show the achievements of this special approach to this Hamiltonian formalism. The Hassan-Rosen transform is derived. No implicit functions are needed, and the geometrical meaning of the coefficients in the algebra is transparent. And at last, my conclusion is that I hope this development of the canonical formalism for bigravity can be useful, because, for example, as you've seen in the from the previous talk by Professor Ashtekar, he first invented the new formalism for general relativity, and then he comes to the latest loop, quantum gravity. So any formalism may be used. This is my hope. May be used in the analysis of Cauchy problem, perturbation theory, numerical bigravity, and who knows, maybe even quantum gravity. Thank you.
Thank you, Professor Soloviev. Thank you. We have 2 questions to you. One comes from actually Professor Ashtekar, who thanks you for a very nice and clear presentation. And he mentions that Speziale and others have shown that the RAM et al. Equations are much simpler and transparent, polynomial without square roots in terms of first-order formulation using tetrads and connections, like in loop quantum gravity.
So this is a remark. I understand.
Yes, this is a remark.
I
Yes,
always agree with this, and I mentioned this work in the list of papers which I have shown you, and I appreciate this paper very much. And when I have done my work, I better understand their work. It was quite difficult to understand it from the very beginning. I'm sorry.
Okay, next question comes from Daniel Blixt. He asks, so these 3 extra degrees of freedom come from that you cannot gauge fix in the second metric?
Yes, not metric, but tetrad, because tetrad has 4 legs, and this gauge is taking 1 leg to be normal vector to the hypersurface. And it is possible to do this for 1 metric, but impossible to do for the 2, because only diagonal rotations of Lorentz rotations are allowed. So
okay.
It's unavoidable, it seems to me, to have them.
Okay, he also asked, but the RAM et al. Gravity should have 5, not 7, right? Or are we thinking of different theories? Also, what do you mean by general big gravity?
Sorry. Degree passed by 2.
You can see the chat, right?
Yes, but
you can see his question.
Gravity is usually, if you are speaking about massive gravity, then you have 5 degrees of freedom. But if you have you are speaking about big gravity, you have 5 degrees of freedom for massive gravity and 2 degrees of freedom for massless gravity. So okay. Big gravity and massive gravity are different theories.
Okay, thank you. And there is a comment from Manuel Hohmann, actually to the comment of Professor Ashtekar. If I remember correctly, the metric and tetrad formulations are equivalent only if the symmetry condition is imposed. So
yes, I am sure it is so. They are equivalent if symmetry conditions are imposed, but here they are not imposed, but they are derived.
Okay, thank you very much. I think we have no time for questions, and of course you can contact Professor Soloviev directly by email. Thank you very much. So we are going to the next speaker, who is Rafael Yunis. Rafael, are you online?
Can you hear me?
Yes. Okay.
Can you hear me? Perfect.
You're going to become a presenter now.
Okay.
Okay, Vladislav, there is a slight change in the program. Kapil Chandra is not going to speak, so we will have your talk right after Rafael's, okay?
Okay.
Okay. You can start. I warn you 2 minutes before the end of the talk.
Okay, thank you very much. Well, I am Rafael Yunis. I'm from a PhD student from ICRANET in collaboration with Sapienza University from Rome. I am going to talk about self-interactions in world matter from the view of cosmological perturbation theory. I'll give you now a little outline of the presentation. First, a small introduction about cosmological perturbation theory and the Boltzmann equations. Then a few insights about warm-dark matter and the role of self-interactions. Then we will calculate the collision integrals for warm-dark matter self-interactions and discuss about the relaxation time approximation. And then talk a little about how to implement this theory in class, a public Boltzmann solver. Now, cosmological perturbation theory describes how primordial perturbations evolve in a perturbed universe metric. These are the relevant Einstein equations right here. We can see that they are sourced by the perturbations to the energy momentum tensor. we need another equation to describe the evolution of these energy momentum perturbations. This can be either an equation of state for species that can be approximated as fluids, or a Boltzmann equation for species, let's say, non-fluid species. This is the Boltzmann equation in general relativity. Usually, in order to solve this, one needs to split the distribution function in terms of the background distribution function and the perturbation. And these perturbations themselves act as sources for the Einstein equation, forming a coupled system. For example, we can have the nice little example of massive neutrinos. The evolution equation for the perturbation is this one right here, without any collision terms. Usually, in order to solve this, one splits it into a Legendre series. The zeroth moment is proportional to the energy perturbation, the first one to the energy flux, and the second one to the shear stress. Now, talking about warm dark matter and self-interactions, we'll first discuss about tensions and alternatives to cold dark matter. There have tensions in recent years to the ruling cosmological paradigm, lambda cold dark matter, most of all in short scales. For example, the missing satellites problem, that there have been historically less observed satellite galaxies to the Milky Way than the ones predicted. Also, these galaxies should be too big to fail to produce stars. And also in the distribution of the dark matter themselves, cold dark matter only simulations show steeper profiles than the ones favored by observations in the center. So one of the few ways we have to solve some of these tensions are, for example, warm dark matter using medium mass particles that are produced more relativistic. These have larger initial velocities and can solve some CDM tensions by erasing structure at small scale at this suppression scale right here. Also, you have the option of doing self-interacting cold dark matter, relaxing the collisionless assumption, using cold and heavy particles, but self-interacting. This solves or alleviates some tension from the way of n-body simulations. This model favor light mediators and relatively large cross-sections. Self-interacting warm dark matter arises as a natural extension from both warm dark matter and self-interacting models. We would propose a light mediator particle, order 1 to 10 keV, and also self-interacting. There are some options on how to proceed from here. For example, you can have models from self-interacting warm dark matter, so sort of arising from warm dark matter models. For example, in production and decoupling of light stellar neutrinos. These favor lower interaction constants, or self-interacting warm dark matter from self-interacting dark matter, trying to distinguishing warm effects in self-interacting and body halo simulations. These sort of approaches favor higher interaction constants. From the point of view of cosmological perturbation theory, the only addition would be a collision term in the Boltzmann equation itself. These can have different expressions depending on the interaction model, the involved particles, etc. So in summary, we presented cosmological perturbation theory, the Boltzmann equation. We presented the self-interacting warm dark matter extension from two different perspectives, and we will present expressions for the collision term in the case of elastic self-interactions. So in the case of elastic self-interaction, the collision term can be expressed in this way, neglecting quantum effects and other things. This is a 9-dimensional integral. It is important to reduce it. We have presented recently a reduced form for this, assuming an ansatz for the interaction amplitude. We have assumed the second-order polynomial in the Mandelstam variables S and T. This is exact for 3-level massive mediator models plus some other models. Now, we have reduced this integral to the lowest exact dimensional integral possible under these assumptions in terms of two kernels, G and K. a whole information about the model is encoded in these kernels. For example, the kernel G only depends on the model itself and the scattering angle. And the kernel K also depends on the energies and the background distribution. A few examples for which this ansatz is exact on tree level are constant amplitude and four Fermi interactions, and also massive scalar mediators, in this case shown for Majorana fermions. Now, we derived an exact approach for this collision term, but this can be approximated further through operator replacing. If we note the fact that the collisions always drive the distribution function to equilibrium, we can propose an operator like this. This is called the relaxation time approximation, with tau called the time scale of the interaction itself. This concept can be used to construct an approximate Boltzmann hierarchy. The collision term is very simple on its first order. We can see it here, and we can construct a Boltzmann hierarchy in this way. This is the exact same Boltzmann hierarchy that for massive neutrinos, but with the addition of this collision. Now, the zero and first collision term are non-conserving of energy and momentum density, so we can set them to zero in order to solve these problems. This is sometimes referred to as the Lorentz model. Now, the time scale of the interactions would be simply the inverse of the collision rate in terms of the, for this case, in terms of the kernels calculated. This would have this neat little expression right here. And now we will speak a little about the background distribution F0. Its evolution equation is relatively simple. It is driven by collisions. This would be the self-scattering we have considered, but also scattering with other particles, production, annihilation of dark matter, etc. Now we will review briefly the concept of decoupling. We usually consider a species to be in thermal equilibrium if its interaction rate is much greater than the Hubble scale. Now we have two scales involved here. The temperature of the coupling of the species with the primordial plasma, this we will refer to as plasma decoupling, and also the decoupling scale of the self-interactions themselves. This we will refer to as the self-decoupling temperature, the self-decoupling scale. Summarizing, we have presented an exact way of calculating self-interaction collision integrals. We presented the relaxation time approximation and the approximate Boltzmann hierarchies. We presented the calculation method for the interaction rate in terms of these exact kernels. And we presented the important concept of self-decoupling. And I will remark that the self-decoupling temperature is different from the plasma decoupling temperature, or what need not be. So we developed a modification to the public Boltzmann solver class. Class is a full linear cosmology solver with a well-developed non-cold dark matter module. We implemented the self-interacting quantum matter hierarchies in this code, and we are particularly interested in obtaining the power spectrum, the linear power spectrum today for these modified cosmologies, and also the CMB and isotropy CLs. Now, let's briefly discuss what this modification does. In the case of the background distribution function.
You have 2 minutes, Rafael. 2 minutes.
Okay. In case the self-decoupling temperature is relativistic, then this background distribution function remains in a relativistic form. But if the self-decoupling temperature is non-relativistic, then as the species is brought to equilibrium form by self-interactions, the background distribution function would move from a relativistic form to a non-relativistic form. So F0 is maintained in equilibrium if the self-interactions are still coupled through the relativistic non-relativistic transition, but the equilibrium itself shifts from relativistic to classical. Also, we have implemented, obviously, the self-interacting warm dark matter hierarchies in terms of the relaxation time approximation, using the interaction rates we can see right here. And we have obtained these results. We have obtained the power spectra for this modified cosmology. We can see in black the cold dark matter prediction, in blue and red, two different warm dark matter models, and over them modified cosmology's self-interacting world of matter. We can see that for the ones that correspond to relativistic self-decoupling, the predictions are equal to their equivalent warm dark matter models. But in the case of non-relativistic self-decoupling, the distributions are considerably colder. So, in conclusion, we have presented self-interacting world dark matter in cosmological perturbation theory under an ansatz for the scattering amplitude. We calculated the consequences of this cosmology in the power spectrum, accounting for non-relativistic self-decoupling. Possibly, we can use this model in self-interacting extensions of models such as neutrino or warm extensions of self-interacting dark matter. Also, possibly massive standard model interacting neutrinos, and we look forward for an exact numerical implementation of these collision integrals and the full background treatment for specific models from production to the late nonlinear stages. Thank you.
Thank you so much, Rafael. I don't see any questions so far. Yes, there are some comments. Nice talk. Okay, therefore, we probably, since we are a little bit in time delay, therefore, I would like to ask the next speaker.
Thank you very much,
Vladislav Stefanov.
I'm here.
Okay. Now your presenter. You can share the screen. Okay. So you have 15 minutes, and I will warn you 2 minutes before the end of the talk. Okay.
Good. Okay. How much? 10? You say 10 minutes?
13 minutes.
13. Okay. Hello, dear colleagues. My name is Stefan Vladislav. I'm from Institute of Physics of Belarus, and I will talk about interesting case of gravitational interaction. Okay. Nowadays,
I don't see your presentation. Sorry, can you put back your presentation? The screen was short a moment.
Sorry.
And disappeared.
Good. Is it good? Do you see it?
No, I cannot see it. Maybe you don't put it full screen, just inside the application. Okay. Okay, now we can see.
You see. Good.
Yes, you can proceed.
Okay. A lot of researchers of gravity interaction at nowadays that we know. It's, for example, gravitational waves experiment, future ELISA experiment, and others. But all of these experiments is all ideas that became real only in recent time. And why? Because the real progress in experimental device, and especially in quantum optics experimental tools and devices. So, but not only old experiment can be implemented now. We also can make experiments with quantum objects, use the same technologies and find how gravity influences on quantum objects. Today I will talk about influence on gravity to quantum interference. And I will talk about the simple model such as time Dicke state. Okay, what is it? First, we have n stationary two-level atom in ground state, and we assume that one photon that we can present as plane wave fall on this ensemble. So when the absorption of this photon is happened, we will have the timed Dicke state. It's state with phase factors that depend on position of each atom, and this is superposition state that describe that consists of n-1 ground atom in ground state and one excited atom, but all of them is intact. We can't find each what atom is excited. So this is time Dicke state, and then we find that this state is spontaneously decayed and emit photon. So we have again the ensemble of n atom in ground state and emitted photon, and this is the state of the system right in that form. So here we have atom transition frequency and spontaneous decay rate. So if we have here summation of our atom, and if we have a big density, a large density of atom in atom close, we can change the summation to integration and find the Dirac delta functions from wave vector of emitted photon with initial, and this is really interesting and surprising fact that that photon that incident photon is equal to the direction of incident photon is equal to direction of emitted photon. It's it shows that real important role of spatial correlation between atomic assembles. So, but what happens if we consider in gravitational interaction here? To answer this, we have the Schwarzschild metric and say that we have a system that placed far away from center of massive body, and then we can take only one direction of gravity is to center of body, and by linearization of this metric, we can linearization of this non-linear term, we can find the linearization matrix, and here we have acceleration of free fall, and only one direction. We in our reference system is parallel to that direction. We have gravity field. So then we solve master equation, use this metric, and in such way we used the vacuum solution and trying to find some addition that linear to gravity parameter A in the same way as the metric. So we have the solution for plane wave in such wave, and find addition to amplitude, to polarization vectors, and to phase of system. Okay, it's analytically this is system has analytically solution, and this is additions to amplitude, to polarization vector, and to phase and for wave vector. Okay, knowing this is all of how the this vector is, what form this vector has, we can try to write Hamiltonian of system in quantum way. So we use quantization operation as usual, and find that all corrections that I told before is reduced, and only one addition is changing the Hamiltonian is changing of volume of field mode due to changing of elementary volume. So using this Hamiltonian, we find the Hamiltonian interaction picture and solve the Schrödinger equation for this interaction Hamiltonian according to Weisskopf-Wigner theory. We have the excited atom 1 and trying to find what states that atom will have what evolutionary state of this atom will have form. So we know that form of this solution will be in slide, and then we can formulate two equations and trying to solve it. Okay, the first is don't change, but the solution for amplitude of ground state is different due to changing of Hamiltonian. We also must take into account that time in that equation is proper time on atom that placed on some haste. So if we want to work with assemble of atom or several independent atom, we must change the reference system to laboratory reference system, and it's possible to do by changing the time of proper time of atom to some coordinate time. So then solution of amplitude for ground state atom will have that form. Here we have the well-known effect of redshift atom transition and changing of spontaneous decay rate. All of this is due to time dilation, is well-known effect of general relativity in sphere of general relativity.
2 minutes. Vladislav, 2 minutes.
Okay, then we write time and Dicke state as in similar to vacuum form, and find that after summation we lose the Dirac delta function for in z direction. We find that in x and y direction that perpendicular to gradient of gravity field is equal, but in z direction is have some spread. So we find that here is Heaviside step function. So we find that emitted photon can have direction that differ from incident photon, and also the frequency will have the frequency of wave package also will spread, and if we calculate it in Earth's laboratory for optical range, we find that this frequency spread is about several hertz. It's really small, but as recent experimental devices can detect it, and this is really a good demonstration how gravity interaction, even in weak gravity field interaction influence to interference and how it's destroyed. Okay, thank you for your attention.
Thank you very much, Vladislav. Let's see, questions. I just would like to mention that this work is performed at the Institute of Physics and also in the ICANET Minsk Center, which was just established a few years ago. It's actively developing. If there are no questions, let's move then to the next speaker, who is Manuel Hohmann. Manuel, can you, okay. Yeah. Yes, you're online. So you are presenter now. Can you share your screen, please?
Okay.
Okay.
You see it?
Yes, you can proceed. Okay, I will warn you 2 minutes before the end.
Okay, thank you very much. So I would like to present some work which is has been done, well, actually last year already, and it is about the so-called post-Newtonian formalism or parameterized post-Newtonian formalism, and it is about the gauge-invariant formulation of this formalism. Let me start with a very brief motivation. We have many experimental tests of modified gravity theories in different regimes, and here I would like to focus on solar system tests and also pulsars. And the classical or most classical test for this is a so-called PPN formalism, which is basically a weak field approximation of a metric gravity theory, which assumes a particular coordinate system and then allows to characterize a gravity theory by 10 constant parameters, which are observable in a solar system. There are different extensions to this formalism. One can look at more fundamental fields than the metric, like a tetrad field, for example. One can look at several diagonal metrics, like in the biometric theory we have seen in this session. And what I would like to focus on here is that we can use a particular formalism, which is the diffeomorphism invariant, which uses geometry basically, and the so-called gauge-invariant higher order perturbation theory. So let me start with a very brief outline. I would like to show you what are these gauge-invariant higher order perturbations, and then a very brief recap of the PPN formalism, and show you how these are connected to each other. So what is the idea of a gauge in this context? So usually we describe a physical space-time, which is a manifold M with some metric, and where we have no canonical choice of coordinates given a priori. And we want to compare this to a reference space-time. So we want to have some manifold with a metric and coordinates assigned to it. And usually we take some highly symmetric standard space-time, like Minkowski space-time or some maximally symmetric space-time, or also the FLRW space-time, for example. And we want to regard our physical metric G as a perturbation of this background metric. But here we immediately see a problem. We have two different manifolds, and so we cannot identify these manifolds canonically with each other. So there are no coordinates in our physical space-time. And so we cannot compare the metric and the reference metric because they live on different manifolds. And the idea how to compare them is we need the diffeomorphism that relates these two manifolds to each other. And only then we can identify points on these two manifolds, and we can compare the two metrics to each other. If we look into perturbation theory, then our physical metric usually depends on some parameter in such a way that the zero value of this parameter corresponds to the reference metric and reference space-time. And so basically for every value of this control parameter, perturbation parameter, we have our own metric on our own space-time. And the idea is to have a perturbation expansion basically in this parameter. Now, again, we have the problem they are defined different manifolds, and so we need to have a gauge, which is now a family of diffeomorphisms. And with this, we can pull back the metric to the reference space-time and then perform a series expansion of this metric. And but the coefficients we have in this expansion, they depend on the choice of the gauge. And the idea of this gauge-invariant formulation is that we fix some particular distinguished gauge, like for example, imposing gauge conditions on the metric, and then define the gauge-invariant metric as the metric in this particular fixed gauge. And we can then translate the metric in any other gauge by relating the metric degrees of freedom. And our metric degrees of freedom split into two parts, the gauge-invariant part and a second part which depends on the choice of the coordinates. And so we have the number of independent components of them is consistent. So this adds up to the full number of degrees of freedom. Now in the PPN formalism, we want to apply this method now. And what is the basis of the PPN formalism? We start from the energy momentum tensor of our matter. For the matter, we assume a perfect fluid, which is then characterized by a few quantities. And we then assume that we have a particular rest frame, the universe rest frame that we choose, which is basically the choice of a gauge. So a particular choice of coordinate system. We can then express all our variables in this particular coordinate system. So take their pullback along this map X. And we assume that the velocity of the source matter in this particular reference system is small compared to the speed of light, which is equal to 1 here in this notation. And then we use the speed of the source matter as the perturbation parameter. Based on the values in the solar system, we can then assign velocity orders or perturbation orders to all quantities, to all matter quantities. And further, we assume that our solution is quasi-static. So any time the derivative of the metric is induced only by the motion of the source matter and therefore gets another velocity order. Now, in the PPN formalism, we assume a particular fixed gauge, so which is called a standard PPN gauge. And in this gauge, we assume that the metric takes a particular form, which is given by these equations. So what are the objects that appear here in the metric? The ones here marked in blue are the so-called PPN potentials, which are basically integrals over the source matter distribution, while the other ones, PPN parameters marked in red here, characterize the gravity theory. So these are constant parameters that depend on the theory. And the idea now is that we can decompose this metric into the gauge invariant and the pure gauge parts by making this choice. So what is now the idea behind the so-called gauge invariant PPN formalism? So now we start with the definition of the metric components in a gauge invariant way. And I will do this by introducing these objects here. On the right-hand side, these are the gauge invariant quantities on which the following conditions are imposed. So there is the objects that appear here are divergence-free vectors, divergence-free, trace-free symmetric tensors, and everything is done in a 3+1 split here already. They are under a gauge transformation, they transform in this way here. And so they are related to the arbitrary gauge ones on the left-hand side, in a gauge X, are expressed in terms of the gauge X on the right-hand side and the gauge invariant perturbations. And the gauge-defining vector fields also split into a divergence-free vector and scalar parts. Now, if we look at this expansion, we can count how many independent components we have at each perturbation order. In the metric and in the PPN formalism, the only important perturbation orders are second, third, and fourth velocity order. And we see that indeed the number of independent components of the arbitrary metric exactly splits into the gauge part and the gauge invariant part. So that is a nice property that we would like to show here. So that means that we can, in this formalism, really separate the physical information from the coordinate choice. So we don't have to make any particular coordinate choice anymore. We have this information already split in two different parts, and so we can solve only for the gauge invariant part. Now, with this relation on the expansion coefficients, if we look what the PPN metric looks like, then we can split it into the gauge part and the gauge invariant part. And we find that the gauge dependent part is given by these formulas here. And finally, the gauge invariant metric components are given by these formulas here. And I will show you in a bit how to apply this then to a particular theory, what these equations look like for a particular theory. Now we need to expand also the field equations of our gravity theory. In order to do so, we need to know what is the source in these field equations. It is the energy momentum tensor, which we also need to split now in gauge invariant components. And we can do this with these formulas here. And we can express these components in terms of the PPN potentials. So they are given as derivatives of the PPN potentials. Then we do the same decomposition of the gravity side, where we have, for example, the Einstein tensor, which are basically derivatives of the metric components. And then we can equate both sides, and we can then read off the PPN parameters in a rather simple way. And to show you how this looks like at a particular example, I have here the example of a scalar field theory or scalar tensor theory, which is basically a Brans-Dicke-like theory with a scalar field that is coupled non-minimally to the curvature scalar. But I assume for simplicity no potential for the scalar field. It is then determined by a free function of a scalar field, which is called omega here. And I assume that we are working in a so-called Jordan frame. Jordan frame means that we have no coupling between the matter and the scalar field. So the metric that couples to the matter is indeed just the physical metric. And if you then calculate the field equations of this theory, and here I have already transformed them a bit to make them simpler, then we arrive at these field equations where on the right-hand side we have as the source term energy momentum tensor and its trace, both as a source for the metric and for the scalar field. On the left-hand side, we have a second derivatives of the scalar field, and we have the Ricci tensor. And now we want to decompose this into perturbations and into gauge invariant equations. And so we need to choose a gauge. And here I have chosen an arbitrary gauge. So this is called X. To derive the equations, we need to fix what are the components of the scalar field that are relevant. Here we find in the PPN formalism that these are exactly the 0th order, which is a constant background value. And we have a second and the 4th order. And with these, we can calculate the gauge invariant decomposition of the scalar field as well, in order to put it into the formalism as well as the metric. And finally, we need to make a Taylor expansion of this function omega around the background value.
You have 2 minutes, Manuel.
Thanks. And finally, we find that the 0th order solves the vacuum field equations, which is important for the consistency of this ansatz. And finally, from the remaining equations, we get the gauge invariant metric. And now we solve these equations. We first need to normalize the gravitational constant, and then we obtain the metric in terms of the PPN potentials, and we can solve for all the components here. And when we then compare with the PPN metric, we find that the PPN parameters indeed reproduce the well-known result. But what I have not shown you is the calculation that sits between these two equations, which is significantly simpler than in the standard PPN formalism. So let me come to the conclusion. I have shown you the principle of gauge-invariant perturbation theory, where we distinguish between the physical and the background space-time, which are related to each other by a particular gauge. I have shown you the basics of the PPN formalism, which characterizes gravity theories by 10 parameters. And I have shown you the basic idea of how to apply these two formalisms to each other and combine them. And the main advantage is that the formalism becomes a lot more simple in the actual calculation. And to demonstrate this, I've shown you a scalar tensor theory. Very brief outlook. One can nicely now extend this formalism. One can go to higher order theories and look at black hole mergers, for example. One can apply it to more general formalisms and include other mechanisms like the Weinstein mechanism. And one can then apply it to many different theories. And to give you just a reference, you can find this work published here under this link. There, I thank you for your attention.
Thank you, Manuel. Thank you so much. We have a question from Andrew Beckwith. The question is, when considering the action and field equations, you left out a potential from the scalar field. In doing so, did you eliminate some potential experimental physics from the assumed data sets in order to simplify the algebra of the derivation?
Yes, so in principle, one can include a scalar field. The only thing that becomes a bit more tricky is that then the potentials change their form. So one does not have the usual Newtonian potential anymore for the scalar field, but since it's a massless field, one then obtains the Yukawa potential, which is not part of the standard for PPN formalism. So one needs to look at an extension of the formalism in that case, with this either with adding an extra potential or with a distance-dependent parameters for the theory. This is possible, and here I have just omitted it for simplicity. But one can include the fields, the potential for a scalar field.
Okay, thank you. I don't see other questions. Therefore, we thank Manuel again. And we are moving to the last speaker of this session, Kiril Maltsev. Kiril, are you there?
Yes, I'm here.
Okay, you are presenter now. Good evening. You are presenter, so you can share the screen.
Yes.
Okay, you can see it. Perfect.
Great.
Okay, you may start. I will warn you 2 minutes before. Okay.
Thank you very much for the introduction. My name is Kiril Maltsev, and I'm a PhD student at the Physics of Stellar Objects group at the Heidelberg Institute for Theoretical Studies. And it's a great merit to contribute to this fourth edition of the Zeldovich meeting on the topic of foundations of black hole thermodynamics. First of all, can I change the slide?
If there are problems with full screen, you can go back to the non-full screen and then try to change the slides. No, it doesn't change. Can you?
No. Okay.
Okay, it works.
Does it work? Okay, excellent. Okay, let's go on like this. So first of all, let me give you a historical overview over some of the landmark publications in the beginning of the black hole thermodynamics research program. And in the following, I will make the following distinctions. When I refer to a classical black hole, I refer to a black hole as it is purely described by general relativity, and the semi-classical black hole as such, where the classical vacuum surrounding the black hole is replaced by a vacuum in quantum field theory, which is source of virtual particle antiparticle pairs which are created and annihilated. And so Zeldovich back in 1970 proposed a mechanism for semi-classical curved black holes to emit radiation on the basis of superradiance, in which the angular momentum plays a crucial role to amplify quantum waves and polarize the vacuum by pulling apart virtual particle pairs that otherwise would annihilate. Then in 1971, Ruffini and Wheeler have shown that the classical horizon constitutes a one-way membrane to information flow. In other words, that whatever crosses the event horizon doesn't come out again. In a series of papers in some of these years, it has also been shown that an increase in classical horizon area is irreversible. In other words, that once the horizon has grown, it cannot decrease back to its previous smaller state. Wittgenstein, 1972, then proposed the generalized second law to resolve the Dirac-Wheeler paradox, which addressed the question what happens to a thermodynamic system such as matter radiation once it crosses the event horizon, and how to deal with conservation of thermodynamic properties. 1973, Bardeen, Carter, and Hawking established the 4 laws of black hole mechanics. And 2 years later, Hawking calculated the spectrum of radiation from semi-classical stationary horizon and concluded that it is a thermal spectrum. This talk will concern the grounding of thermodynamic significance in the laws of relativistic black hole mechanics. And to disperse to it, I will draw an explicit distinction between the phenomenological definition of temperature and statistical mechanics, as we know from classical thermodynamics, and the statistical definition of temperature and entropy, as we know from statistical mechanics. And then in the next step, we will check whether these definitions apply in the case of black hole mechanics. So let's start with an outline of the 4 laws. The 0th law of thermodynamics, let me recall it. It introduces the concept of a thermal equilibrium. When 2 systems in thermal equilibrium with the third are in thermal equilibrium with one another, then it allows us to introduce a constant temperature. The counterpart in black hole mechanics is that the surface gravity is constant across the entire event horizon. The first law of classical thermodynamics relates the differential of the inner energy with the heat and work differentials. And the counterpart in relativistic black hole mechanics is that any change in black hole mass is counterbalanced by a change in surface area or a change in angular momentum of the black hole, with kappa and omega denoting the surface gravity and angular velocity. The second law of phenomenological thermodynamics demands that for a closed system, the entropy change cannot decrease. And the counterpart in black hole mechanics by Hawking's area theorem states that the area of the surface of the horizon can only increase. The third law of thermodynamics states that the 0 point of temperature is not achievable by any process within a finite number of steps. And the counterpart in black hole mechanics is that extremal black holes are forbidden. In other words, surface gravity equal 0 is not achievable within a finite number of steps. So what can we learn about this with respect to thermodynamic analogies? From the second law, we see that the horizon area plays a role analogous to entropy. And from the 0th and 3rd law, we learn that the surface gravity is analogous to temperature. From there, we can also look further and at the first law and see that the heat differential has got its analogous analogy in the surface area differential times the surface gravity, and the work differential of ordinary thermodynamics has got its counterpart in the differential of angular momentum of the curved black hole times its angular velocity. And now again, let me recall the central question: are the laws of black hole mechanics endowed with genuine thermodynamic significance that go beyond pure mathematical analogy? And for this, we will look into the temperature and entropy definitions. We will start with the phenomenological definition, and there are 3 aspects of it entailed in the phenomenological sense as given by classical thermodynamics. First, it is a characterization of heat flow. Second, it reflects a capacity of a system to perform work. And third, it acts as a quantifier of efficiency in a reversible Carnot cycle. So let me recall that Clausius introduced temperature in order to quantify efficiencies in a Carnot cycle, so that temperature is always bounded to efficiency measures in a thermodynamically coupled systems. And let me quote Sommerfeld on this. Thermodynamics investigates the conditions that govern the transformation of heat into work. It teaches us to recognize temperature as the work value of heat. Heat of higher temperature is richer, is capable of doing more work. We may now ask the question, is phenomenological temperature well grounded when we apply it to black hole mechanics? And doing so, let us distinguish between the scenarios of a classical Schwarzschild black hole, a classical Kerr black hole, and a semi-classical Schwarzschild black hole. In the case of a stationary Schwarzschild black hole, the answer is no. And this is for the reason that a Schwarzschild black hole is a perfect absorber, which does not emit anything. And if it is perturbed, however, the scenario is different. A perturbed Schwarzschild black hole will be a source of gravitational radiation, and there is possibility to use the gravitational radiation as heat to power a heat engine in the Carnot-Garock cycle, which has been a theoretical construct but never fully worked out. So the answer is possibly not yet. The scenario is similar for Kerr black holes. However, the process which would allow it to couple to ordinary thermodynamic systems to extract energy from it is the Penrose process, where the rotation energy of the associated with the Cauchy horizon is used to power a heat engine and extract it from the ergosphere. And such a construction would be a Carnot-Penrose cycle, but it has never been fully constructed. So the answer is, again, possibly and not yet fully worked out. Finally, for the semi-classical Schwarzschild black hole, the answer is positive. And this is on the basis of the Zeldovich-Hawking radiation pressure, since the flux of outward directed particles from the radiation generates a pressure which even already in classical sense will couple to thermodynamic systems, since whatever system you couple to it, it will feel the flux of particles even though the pressure will be low, and thereby power a machine. And such a cycle in the following will be called a Carnot-Hawking cycle. Let's move on to the statistical definition of temperature. And there are three aspects entailed. First, it is a measure of an ensemble of electromagnetic fluctuations. And their properties are such that they exhibit black body radiation, at least in the equilibrium. And the mean value of the statistical temperature is encoded by the peak of the spectrum of the black body radiation. So we may now again ask, how about the statistical temperature? Is it well grounded in the case of the black hole? The answer is no for the purely classical black hole, Schwarzschild or Kerr, for the reason that there is no way to introduce an ensemble of fluctuations if one purely relies on a classical description of black holes. In the case of semi-classical Schwarzschild black holes, the answer is yes, and for the reason that the spectrum of the fluctuations originating from the horizon is thermal. So now let's move on to entropy. In the phenomenological definition of entropy, there are three aspects entailed. First, it is a measure of how much energy is required to transform heat into work. Second, it is a function of state of a thermodynamic system, a Carnot cycle. And third, it is a quantifier for the second law. Clausius introduced entropy to characterize a Carnot cycle and quantify efficiencies. And as a quantifier for the second law, it allows to differentiate between reversible and irreversible processes. Let me quote Clausius' statement on the second law: heat can never pass from a colder to a warmer body without some other change connected therewith occurring at the same time. And the Kelvin-Planck statement, which has been formulated later: it is impossible to devise a cyclically operating heat engine, the effect of which is to absorb energy in the form of heat from a single thermal reservoir and to deliver an equivalent amount of work. So let's ask the question, is the phenomenological entropy well grounded? For the Schwarzschild black hole, if it's stationary, the answer is no. There is no way to extract any sort of radiation or a form of heat from the Schwarzschild black hole, since it is a stationary perfect absorber. If it's perturbed, again, the situation is different. Work could be extracted from the gravitational radiation, as has been mentioned before. And similarly, in a Kerr black hole, the rotational energy could be used to quantify heat transfer and power a heat engine in a Carnot-Penrose cycle. For the semi-classical Schwarzschild black hole, the answer is yes, if we adopt two assumptions. First, the validity of the generalized second law, and second, the viability of the Carnot-Hawking cycle. And let me recall what this amounts to. The generalized second law states that for the joint system of horizon area of the black hole times a constant plus the ordinary thermodynamic entropy associated with the surroundings of the black hole, the sum of it is non-decreasing. And the Carnot-Hawking cycle, unfortunately, I cannot go into the details of it, but it consists of a coupled system, Schwarzschild black hole plus photon gas surrounding it and enclosed in a box, and with two ideal heat baths. And the joint system undergoes reversible changes as they would in a standard Carnot cycle. And given the restricted parameter value ranges upon which the quasi-static equilibrium between black hole and photon gas can be maintained, the thermodynamic meaning of the Bickenheim-Hawking notion of a black hole is rigorously well defined upon the efficiency of the reversible quasi-static Carnot cycle. So let's come to the final part, the statistical definition of entropy. There are three versions of statistical entropy already in statistical mechanics. The Boltzmann entropy is the measure of the sum of combinatorial ways a given macroscopic equilibrium state can be represented by non-interacting single particle microstates in phase space. The Gibbs von Neumann entropy is the measure of the probability distribution defined in state space of all the possible interacting many particle microstates for a given statistical canonical ensemble. And finally, the Shannon entropy is the measure of the amounts of missing information to fully specify a given macrostate. So finally, we can again ask, is statistical entropy well grounded when we apply it to black holes? For the classical Schwarzschild and Kerr black holes, the answer is no. Again, for the simple reason that there no statistical ensemble can be given by a purely classical general relativity account of black holes. For the semi-classical Schwarzschild black hole, the answer is differentiated. If one has the Boltzmann view, then it has yet not been established. What one would require is something like a unified theory to exploit all the possible configurations in state space by a single particle microstate. If the Gibbsian account is demanded, then what misses is the appropriate statistical ensemble over which the probability distribution is defined. And so as it reasonably connects to the Bickenstein-Hawking entropy formula relating it to the area. And if the Shannon version is taken, then the answer is yes. However, it is a debated one. Hawking's proposal is to use the number of possible internal configurations that are accessible to the black hole accessible to the no-hair black hole. And Kip Thorne's view is that of the number of possible initial states giving rise to the no-hair black holes. In other words, all the possible initial conditions of a collapsing star that would give rise to a black hole finally. So the summary of this talk is that interesting prospects arise already from applying purely classical accounts of phenomenological temperature and entropy, for which a perturbed Schwarzschild black hole and a Kerr black hole have the potential to grant a thermodynamic meaning. And for the case of semi-classical Schwarzschild black hole, the foundation of thermodynamic significance is at an advanced stage, except for the statistical entropy account, which is a debated topic. And so far, only the Shannon version of it has been established. And the conclusion is that the establishment of bona fide thermodynamic significance in the laws of black hole mechanics is an ongoing research program, which has partial success. And even for purely classical black holes, there is an interesting prospect for grounding their phenomenological temperature and entropy in a Carnot cycle. And Zeldovich's merit consisted in being the first to propose a mechanism for semi-classical black hole horizons to emit radiation, although he did not ascribe any thermodynamic properties to it. The link between Zeldovich-Hawking radiation and statistical temperature was achieved by Hawking. And here you find some of the references I used. And I thank you for the attention.
Thank you, Kiril. Thank you very much. Let's see if we have any questions. Okay. Professor Ruffini is asking, is commenting, apparently interesting, but the relation between the surface area of the black hole and the irreducible mass was established in the paper of Christodoulou and myself in 1971. I don't think I didn't see this paper in the reference list you show.
Wait, how can I escape the view so that I can see the comment? Here. Okay. Yeah.
You can see already.
Yeah, I see. But the relation between the surface area of the black hole and the irreducible mass was established in the paper of Christodoulou and myself.
Professor Ruffini this morning mentioned this paper in his presentation.
Yes, so the irreducible mass can be used for the Schwarzschild black hole and the Kerr black hole alike to quantify the amount of free energy available to extract from the black hole. So in the first case, if the Schwarzschild black hole is perturbed, there will be free energy available on the basis of the gravitational radiation. And if the black hole carries angular momentum, then the reducible mass will have components from the rotation energy. So it is a nice. So is it a question or?
It's a comment.
Yeah.
I guess. Now there is a question about from Ivan Sivtsov. What is your view about the information loss at singularity?
So the information loss is the problem that Hawking has been trying to solve all his lifetime since the end of 70s. And so first of all, the information loss does occur if you consider that the semi-classical black hole mechanics is valid all the way down, and there's a question of whether this is a viable approximation at very low black hole sizes, because arguments have been proposed that it's such extreme scenarios where you have strong gravity and quantum field theory coupling to one another, then the semi-classical approximation to black hole mechanics is not applicable anymore. And at the same time, so therefore, the question of information loss may not be answered by a purely semi-classical account of black hole mechanics. The same is with the singularity. According to so the semi-classical approach does not make any statement about the singularity, and some versions of classical approaches even manage to resolve it by adding extra assumptions, but it is a long and broad field, and I think there is no concise answer to this question, whether information loss occurs and whether there is a singularity given the state-of-the-art semi-classical approximation to black hole mechanics.
Thank you. And maybe if I may ask a question from my side, just to summarize in your talk, if Hawking radiation does not exist, does it imply that there is no correspondence between thermodynamics and black hole mechanics?
So my argument over the talk was that the reverse is true. That even without Hawking radiation, even without the quantum effects, we already can argue for thermodynamic properties of the classical black hole. It is on the basis of the fact that one could couple a thermodynamic system to the black hole and use either its gravitational radiation when it is being perturbed, or its rotational energy to construct a Carnot cycle, which I either call the Carnot-Garock cycle or a Carnot-Penrose cycle, which, however, never been fully worked out in theory, to fully justify classical thermodynamics notions of temperature and entropy associated with the surface gravity of the black hole and its area.
Thank you. There is one more question, probably the last one. Ben is asking, is there any relevant experimental observation?
So there have been analog systems, which it depends, of course, what you mean by experimental observation. If you refer to the Hawking radiation, then actually this year, 2020, there has been an interesting publication that a metallic cylinder was used to mimic the superradiance in a classical system, as has been demanded by the Zeldovich effect. And with regard to the Hawking effect, there have been analog systems designed by Steiner, a scientist in Israel, using acoustic waves, where you have trapped subsonic and modes, and they one can so to say excite them to become supersonic, so that trapped acoustic waves can escape a cavity and thereby provide an analog system which would behave like a semi-classical Schwarzschild black hole, where you have trapped modes and they manage to escape using the tunneling effect.
Okay, thank you very much. I think the time does not allow us to go on with questions, so any interested participant can ask the question by email. And I think we have to close the session of this afternoon. And I invite all the participants to join us tomorrow morning at 9:30, where there will be a session, very important session on space missions. The first speaker will be Rashid Sunyaev, the closest collaborator of Zeldovich. And have a good evening, everyone. See you tomorrow. Thank you very much, all the speakers in this session.